Hello, ladies and gentlemen. I hope you are well today. Thank you very much for joining us for our presentation on a streamlined approach for campus bus routing within Simio. My name is Yusuke Legard and I work for Mozamtek. Mozamtek is a dedicated modeling and simulation consulting firm that has been established for nearly 10 years now. We have completed over 300 simulation projects and worked with over 20 Fortune 500 clients. We have also worked in a variety of industries ranging from mining to pharmaceuticals. We are able to provide software advice, training for companies that are looking to build an internal simulation capability, and end-to-end simulation consulting, helping with both model development and analysis. This presentation will focus on both the business need that NIH encountered for a simulation model of their shuttle bus operations and the technical aspects of Mozamtek's implementation approach. Now, a brief introduction to the speakers today. Like I mentioned earlier, my name is Yusuke Legard. I graduated from Duke University with a BS in economics with a finance concentration. I started my career as a simulation consultant with Mozamtek in 2018 and have worked with the National Institute of Health on a variety of projects throughout this time.
Hi, I'm Amy Greer. I'm a simulation consultant with MOSIMTEC. My background's in industrial engineering, and I've been focusing on simulation modeling since 2004.
Hi, and I'm Joe Wolski. I'm the industrial engineering team lead with the Office of Quality Management, Office of Research Services at the NIH. Pre-COVID, our main campus sees about 40,000 employees, contractors, visitors, and patients each day, and operates like a university campus or even a small city. Once people arrive at campus by personal vehicle or regional public transportation, transportation throughout the main campus and satellite campuses is provided by a shuttle system utilizing vehicles like you see here. The system operates throughout a fixed number of stops and fixed timetable, and the map you see here is an example of one of the routes throughout our main campus. Our challenge is to ensure that the system is designed so that capacity aligns with demand in an economical way. We don't want a system that has buses that are too large or stops too frequently. And likewise, we do not want to have overcrowded buses in situations where passengers are waiting for an inordinate amount of time for transportation. Furthermore, the COVID pandemic has placed additional constraints on our system by ensuring appropriate capacity limitations and physical distancing to ensure the health and safety of riders in vehicles. Demand for these services changes within the day, from day to day, and of course presently, with all the systematic changes that the physical workspaces are experiencing due to the COVID pandemic. Having a flexible and robust planning tool that can be used to better understand the impact of our design decisions as we plan for how individuals will return to the physical workspace has been extremely valuable.
Here is an overview of the shuttle bus model that Mozamtek developed for NIH. In the facility view, we can see the NIH campus and the routes of the buses that travel through the campus. All routes on campus are to scale. The route for our off-campus route has an input of the length on the road instead, so that the distances do match the real-life system. We also have an input and output section that provide real-time feedback for the user in the progress of the model. Here's a short demonstration of the animation as we see the first bus of the day. Each bus has a label on the roof that provides a real-time count of the number of passengers on board as well as the capacity utilized. In the inputs, we have the ability to define the schedule for the routes and their buses, as well as each bus's shift information. Other information, such as the hourly probability that a passenger selects a particular bus stop to begin their journey, as well as their destination, is also possible. The capacity of a bus can also be altered. An example of why this would be a useful function is in the era of COVID-19 and social distancing. There may be limited capacity on board buses. Thus, NIH must know whether demand can be serviced or if buses are needed. The Results tab provide in-depth insight to information such as a bus's capacity utilization and the waiting time and travel time of passengers. Our dashboards also allow for a visual representation of the results to help understand the daily pattern of the operation. Here, we view the number of passengers boarding buses by hour, and it is even broken down by stop. This way, the user can understand where and when peak demand lies. So that is a brief overview of the NIH Shuttle Bus Model developed by Mozamtek.
We wanted to talk a little bit about the technical approach we took in this model. There are two areas that we think really enabled building this model quickly and giving NIH a model where they were able to quickly reconfigure inputs and get the answers they wanted. I'll first talk about one of the data structures we used, and then he's going to talk a little bit about the benefits of building custom classes. The key data structure in this model was really the bus route schedule. We couldn't just passively have buses routing through the system. Passengers were too smart for that. Passengers are going to look on a schedule and say, I'm going to wait for 3 minutes so I can get on a bus that gets to my stop very quickly. They're not going to get on a bus that goes 60 minutes out of their way to eventually get to their stop. And if we didn't have the passenger logic correct, then our wait times were going to be underestimated, our time in system would be overestimated, and our bus utilizations by route would be incorrect. And since NIH was really looking at how should we potentially change bus schedules with new demand patterns, all three of those outputs were really important for us to get right. This is an example of one of the bus schedules. This is actually the red line. This reflects multiple buses going on concurrently in the system. And this is one of the challenges with the model. If we had 3 buses, you might see something on the schedule every 5 minutes. But if we went to 1 bus later in the day, you'd only see a stop on the schedule every 15 minutes. So we really needed a way for NIH to be able to generate those schedules on the fly without having to manually go into Excel and actually generate true schedules out. So one of the things we did is we had a table for route building blocks. This would be if 1 bus is looping through the system. This would be how long we would put on the schedule to allow between stops. That both accounts for travel time and loading unloading times. And then once every route has their building blocks, we also have the buses themselves. This is a flexible table. Both of these tables are flexible, but NIH can add additional buses. They can change the bus type. They can change how long the bus is running. So right now with Campus Bus, this is data from pre-COVID. So we had 1 bus started at 6:30, 1 started at 6:45. Basically, these buses ran throughout the day and they were offset by 15 minutes. But using this data structure, you could have 3 buses for morning, drop down for 1 during the middle of the day, go back up to 2 for later in the day. So really just a lot of flexibility in these inputs for whatever NIH wanted to test. Once those structures were set in Excel, when the Simio model started, the Excel data would be automatically uploaded into Simio, and the model initialization code would convert those simple tables into an array structure, and every single bus in the model had its own schedule. It knew what stops it was going to, what time it needed to be at those stops, and if the stop was a time check or not. The advantage of having all of those arrays built out for the bus is the bus logic became very, very simple. This process here is probably our most complex process in the whole model, and you can see it's still a pretty small process. In here, passengers can look for their optimal buses. They can board a bus if they feel like it's optimal for them. The bus can wait if it's a time check or not. It'll dwell until their time check's over. It'll continue to load passengers as long as the time check has not passed and as long as passengers continue to be there. And then once it's done with this stop, it just very simply increments a counter and we go to the next step in the array. So this is a really powerful model that NIH had a lot of flexibility in the input data, but the code under the hood was very, very simple because we spent our time focusing on building out the data structures during initialization to make the rest of the code very simple.
So I'll be providing some insight into the benefits of modeling from scratch. One is the faster development time. By creating custom personalized objects, we are fitting them to our purpose. By using the pre-built objects, one would be trying to fit a square peg into a circular hole. This means that more time is necessary to ensure the desired functionality is in place for our model if we use pre-built constructs. We will compare the logic needed to route a bus towards their destination when met with multiple options. In the image above, we have a bus approacher node that has multiple possible paths out of it to direct the bus to its destination. We will compare the process logic between a custom node and a pre-built node, and why customizing an object helps with the debugging process in a model. In the top image, which is the logic used in the custom node, only 3 steps were required to route the bus to the correct path and to its destination. Whereas in the pre-built nodes, it has a longer process and more steps that can possibly be executed. This means that during the development phase of the model, if issues arose, one would be able to debug the model easier to identify the issues and faster to resolve such issues due to the fact that the custom objects allow for concise and purposeful steps. Whereas in a pre-built object, one would have to teach themselves the logic already present, then identify what steps are used and redundant before identifying and resolving a bug in the model. With customized objects that include only the code and functionality desired for the model, it means that objects are more lightweight. Thus, models are able to run faster. For example, the NIH Shuttle Bus Model is designed to simulate a 24-hour period and run this fast. The faster the run speed not only allows for immediate feedback, but also allows for multitude of scenarios and replications to be run simultaneously in the experiment window. Thus, optimal solutions can be found faster. The customization allows for all code to be labeled with easy to read and purposeful documentation. This means that any future user can pick up the model, study, and understand the underlying code within each object, knowing that all processes in the model have a specific purpose and so does not need to concern themselves of whether a process is used or not. This would be the case if one were using pre-built constructs. Furthermore, due to the ease and opportunity for better documented code, it does mean that future users have greater flexibility and ease to update and change the model where necessary. For example, here is the process logic within a bus entity in the NIH Shuttle Bus Model. As you can see, processes are categorized by the overall functions a shuttle bus goes through during a model run, such as boarding and disembarking passengers. Each process also has an overall comment that tells users how the process in question is triggered, as well as a description of the process's function. Each process step within the process has meaningful labels, thus allowing any user to immediately understand how each step is utilized. This ease of documentation allows future modelers to pick up the model, quickly study the current logic, and then implement any additional updated logic they desire, thus having greater flexibility in the future changes. So to wrap up this presentation, here are some summarizing points. Spending the time to plan smart data structures and implement initialization code greatly reduced overall project time requirements. Just because pre-built constructs are available, it does not mean that they are the best approach for every model. Now, that does not necessarily mean that every single model should not use these pre-built constructs. There are multiple things to consider when deciding whether to use them or not. Such factors include the modeler's proficiency in the modeling program, as well as comfort in creating a personalized object. It also depends what exactly the operation is being modeled. It is possible that every single functionality included in the pre-built construct is needed, thus making the pre-built construct necessary in the development of the model. If you have any questions for us, please do join us in the Q&A session following this video presentation. Or if you'd like to learn more on this topic or about Mozamtek as a whole, please do visit us at our virtual booth or our website. Thank you very much.